Welcome to Math with EJD. In this video, we'll be talking about Laplace transforms for differential equations in control systems. Okay, again, we have said it many times that the Laplace transform is powerful, so I won't stop saying that. The Laplace transform is a powerful tool. Don't be tired of hearing that. It's a powerful tool that converts differential equations into algebraic equations. This transformation is particularly useful. So you can see it's useful in different areas. It's particularly useful in control systems to analyze and design systems. Okay. The Laplace transform, as you know already, if you have been following the other videos, the Laplace transform simplifies the process of solving differential equations, particularly in the context solving differential equations, particularly in the context of analyzing system dynamics, such as stability, response, stability response, and transfer functions, and transfer functions. Okay, so let's move on to talk about Laplace transform of common functions. I mean, we've come across this a lot, but just to refresh our memories, Laplace transform of common functions. Okay, so of course we remember for constant function, we have L of 1. You know, if you have any constant, that would simply be the constant, the number over S. Number two, we have first derivative. So if you're talking about differentiation, first derivative is simply um, L f prime of t, right? And that will be the same as S fs minus f of 0, initial value. Then we have the next one, second derivative. Second derivative. For second derivative, we have the Laplace of f prime prime of t, okay, and that is equal to s squared because it's the second derivative f of s minus s f of 0 minus f prime of 0. That is second derivative. Then number four, we have exponential function. Exponential function. So for exponential function, we have Laplace of e raised power at, and that will end up being 1 over s minus a. Okay, so if you have e raised power minus at, that will be 1 over s plus a, basically. So, and in all right, we have it the of course in all these other cases, f of s. So we can just say where f of s, wherever f of s appear, is the Laplace transform, the Laplace transform of f of t. Now, moving on, we have let me switch again. Now, let's talk about application, application of Laplace transform to control system differential equations. Control system differential equations. Okay. So consider a simple first order linear system with the following differential equation. The following differential equation. So we have tau dy of t dt plus y of t equals k u of t. So here, y of t is the output of the system. The output of the system. We have u of t is the input of the system. U of t is the input, the input to the system. And we have tau and k. These are some constant. Tau and k are constants. So they are time constant. Tau is time constant and k is gain, respectively. Okay. So what do we do with this? Step one. So the first thing we do is take the Laplace transform. Take the Laplace transform of both sides. So if you look at that again, we have the Laplace of tau dy of t dt plus y of t, and that is Laplace of k u of t. Okay. Now, if that is the case, we can split things up. So tau is constant, so we can bring out tau. So we have tau into the Laplace of, that's more like, that's dy of t dt. Then, then the other one is we have the Laplace of y of t, which is more straightforward. And lastly, we have k comes out, which is constant, into the Laplace of u of t, the input into the system. So with this now, we can do this. Tau now is, so dy of t dt, we do that is simply, if that we can take that as y of s, right? So this would be s y of s minus y of 0, being first order stuff. So if you don't know y of 0, we can just keep it this way. And then here, Laplace of y of t is simply y of s again. And this is k. U of t, we can take u of t to be u of s. Okay. So with this now, we can solve for y of s. That's step 2 now. Step 2, we solve for y of s. Okay, so from what we have up there, so we have tau into s, y of s minus y of 0, k, plus y of s again equals k u of s. So this means we have tau s y of s minus tau, let me write that well, minus tau y of 0, okay, um, okay, this is plus actually, plus y of s equals ku of s. So y of s is here and y of s is also here. So we can put them together. So we have y of s into tau s plus 1, the one that comes from here, minus tau y of 0 equals ku of s. Okay, so that means that y of s into tau s plus 1 is equal to um, ku of s, ku of s plus tau y of 0, so that y of s, which you are looking for, is actually ku of s plus tau y of 0 all over tau s plus 1. So this is what we have in that case. So this is the Laplace domain representation. So this is the Laplace domain representation. This is the Laplace domain representation of the system. So we can go for step 3. So in step 3, we just have the inverse Laplace transform. So we take the inverse Laplace transform for what we got up there. So to find the time domain response, the time domain response, we need the inverse Laplace transform. Okay. So if u of s, the input, if u of s represents the Laplace transform of a step input, which is u of t equals 1. Okay, that is, we now have u of s equals 1 over s. So the equation becomes, the equation becomes so we're taking, the equation becomes let me see now. Okay, this is the only u of s here, and this s is actually constant. And that is supposed to be, okay, u of s is now 1 over s. Yeah, that's the idea. Okay, so the equation becomes y of s equals k 1 over s plus tau y of 0 all over tau s plus 1. Okay, that's what that becomes. So now performing partial fraction decomposition, partial fraction decomposition, and taking the inverse Laplace transform, we get the time domain solution, the time domain solution y of t. Okay, so based on what we've done before, right? This can also be another practice. Okay, this can be another practice. Get y of t. Okay, get y of t. So what we have to do there is split it up, do partial fraction. So there's something about the s you have to sort out. You have to make sure everything s is down there, and then you can do partial fractions and get it out. So let's see. Should I do that now? Should I do that now? I don't know. Yeah. So Okay, let me just tidy it up a little bit so that can it can be easier. So now I have y of s equals, so this is more like k of s plus tau y of 0 all over tau s plus 1. So this is like y of s now equals, s is common at the top there. So that's k plus 1 in s is s. So we have s tau y of 0. And down here we have tau s plus 1. Okay. So so this is more like this whole thing divided by this. So the both of them will be down. So y of s now is equal to k plus s tau y of 0 all over s into tau s plus 1. So now this is easier to handle. So this is, now you can see this as the main practice now. So practice again, get get y of t. So this is just it's a linear thing. So just say a over s plus b over tau s plus 1 because they're both linear, and then try to get what y of t should be for this. Okay. Um, so the next thing is to, so let's talk about control systems. So let's talk about uh an example of transfer function. Example of transfer function. So here, the transfer function, the transfer function g of s of the system is the ratio of the output to the input in the Laplace domain, in the Laplace domain, okay, and that is g of s equals y of s all over u of s. That's the same thing as k all over tau s plus 1. So this is the transfer function. So this function provides a model, of the system's dynamics and can be used to analyze stability, frequency response, frequency response, and design controllers. All right, so in conclusion, the Laplace transform allows the conversion of complex differential equations into simple algebraic equations, making the analysis of control systems more efficient. By using the Laplace transform, we can easily derive transfer functions, solve for system responses, and study system behavior in both the frequency and time domains. So don't forget the simple practice now. So just, you want to get y of t from here. So get y of t. That's the practice. Let me see this in the comment section, either on YouTube or on Facebook. So, and what you are simply going to do is resolve into partial fractions and take the Laplace inverse, basically, and then you can get the y of t. That's the output, right, in the control system. So let me also know in the comment section how helpful these videos are for you. And if you want to teach a topic or solve a particular problem, so please just go ahead and let me know. And of course, if you have subscribed to this channel, thank you. If you have not, please go ahead because you'll be missing a lot. Go ahead and subscribe. And of course, do not forget to hit the notification bell so you can always get alerted each time a new video is released. Then be sure to like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.